welcome you to the Dallas Independent School District STEM Environmental Education Center for our virtual field trip. Special thanks to Rosemont Upper Dallas ISD. If you're watching and you have not signed up, please do so. Go to www.tiny.cc/6-8 registration and sign up. That's just for our number count, please. Thank you very much. The program today will be atoms and the periodic table. During this virtual field trip, students will observe the structure of atoms. Students will learn the protons determine an element's identity and valence electrons determine its chemical properties, including reactivity. Students will also interpret the arrangement of the periodic table, including groups and periods, to explain how properties are used to classify elements. Mr. Monroe will cover the history of atoms, Mr. Dominguez, the structure of atoms, Ms. Schramm, protons and valence, and Ms. Ramirez will tell you all about the periodic table. You cannot ask us a verbal question during this program, but you can go to www.tiny.cc/question.answer, and we will try to answer during the program. And if not, I will send the answers to your teacher and they can share with you. Now I'm going to stop sharing my screen, and Mr. Monroe is going to tell you all about the history of atoms. That is Mr. Monroe.
Good morning, students. My name is Mr. Monroe, and I'm going to be taking you on a little trip back in time about the development of atomic theory. Now, later on today, on your virtual field trip, you will be learning about the structure of the atom. And we have come to this point in the study of the atom. It started a very, very long time ago. In fact, I will tell you this. It started so far back, I guess you would say well over 2,000 years ago. There was a fellow by the name of Democritus, and he was a philosopher. And it's really funny how scientists during that age weren't really called scientists. I guess they wore the brand of being a philosopher. Now, what I'm going to do, I'm going to need to share my screen with you for a short presentation about some of those famous people that did the research that has brought us to the point where we're at right now about understanding the atom, so the history of the atom. Important experiments leading to atomic theory. Atomus. Oh, Democritus. Oh man, he came up with the first idea that everything that was made up of matter, and you can see this is well over 2,000 years ago that he was here. He was a Greek philosopher. He was the first person to think about an atom's existence. He believed that matter was composed of tiny invisible particles called atoms. He had no experimental evidence to support his thoughts. So that's probably why back then they were called philosophers. Now, before we get to John Dalton, I want to tell you that Democritus, his idea about the invisible particles kind of clashed with another well-known philosopher by the name of Aristotle, because Aristotle believed that the elements that existed here on our planet, either they were earth, water, air, or fire. So it kind of contrasted that. So then came along a fellow by the name of John Dalton. That's what he looked like. Actually, he was a meteorologist, and we know that a meteorologist is a person that studies the Earth's atmosphere and weather-related activities that go on in our atmosphere. And unlike Democritus, he had experimental evidence to support his theory. Dalton had four major points to his theory postulates. First of all elements are composed of invisible particles called atoms. Atoms of the same element are identical. The atoms of any one element are different from those of another. Now, Dalton's theory was this. atoms of different elements mix or combine in whole number ratios. Oxygen combines with hydrogen to form water in a 2-to-1 ratio. Chemical reactions occur when atoms separate, join, or rearrange. In a chemical reaction, atoms of one element never change into another. He had what they call the cathode ray tube experiment. Now, this is the guy that brought that around, and that was somewhere between early 1900s. This is what he looked like. Very distinguished looking gentleman. And that's what his cathode ray tube looked like. In the tube was an inert gas and two plates, a positive and a negative. The particles in the gas were attracted to the positive plate. Therefore, the particles must have a negative charge and the opposite to attract. J.J. Thompson was another fellow. He discovered the electron. From his experimental evidence, he believed that the atom was a solid positive sphere with electrons shoved into the sides of it. His model was said to resemble the popular English dessert called a plum pudding. And so his model was deemed the plum pudding model. Looks something like that. And that image there is actually an image of the plum pudding. Looks kind of delicious. Then along came Rutherford, and he looked like that. Distinguished looking gentleman. He used the gold foil experiment to discover the nucleus. He shot high energy beam of alpha particles into gold foil, as you can see in this image. He had a radioactive source, and he had lead that was involved in protecting that area. And then you can see that the alpha particles were ejected or shot into the tin foil. And it was called the gold foil experiment. Rutherford's conclusions was this. His observation was most of the alpha particles went through the gold foil experiment. The atom is mostly empty space. That was his conclusion from that. Few particles were deflected at small angles, he concluded. The alpha particles came close to something small and positive in the nucleus. The alpha particles hit the small, very dense, and positively charged center. Very rarely, particles were deflected at large angles, he concluded. Then came Goldstein. Goldstein discovered the proton. And then another scientist came along by the name of Chadwick, and he discovered the neutron. So there we have it, students. The development all along of what we call atomic theory. Now, the current atomic theory states that are regions inside an atom where electrons are likely to be found, and this region is actually referred to as the electron cloud. Now, listen, guys, if any of you have any questions, I'm going to turn it back over to Dr. Gorman, and I bet he can answer those questions for you. You guys have a good day.
Okay, we did have a question, Mr. Monroe, and that was a very long and distinguished list of scientists or philosophers, but who was the one that started? It was Democritus, and it was in 400 BC. And now we're going to let Mr. Dominguez tell us about the structure of the atom.
Hey guys, it's Mr. Dominguez here with the EEC, and in this portion of your virtual field trip, I will be talking to you guys about the structure of the atom. Now, atoms are incredibly small things, and it's kind of hard to fathom them having parts that make up their structure, right? Because atoms are so small that if you were to take a sheet of paper and you were to take a look at its width, and as you can see, it's razor thin, right? Super, super thin. And if you were to stack some atoms on top of one another from the bottom to the top of this width, it would take about 1 million of those atoms to reach the top. So it's kind of hard to imagine a particle that's smaller than the atom, but the atom is actually made of three particles, the proton, the neutron, and the electron, that give it its identity. So we're going to make a model to show you that structure today. It will be a drawing as I draw each subatomic particle that makes up the atom. I will explain to you exactly why that part is important and how it affects an atom's identity. So let's get started with the structure of the atom. All right, guys. So before we get started with our drawing of an atom, I would like to clarify just one thing, because you guys might have seen this wonderful thing called a periodic table, either in your classroom or in a textbook, or on a science show, whatever. And you may be wondering, are elements and atoms the same thing? I've heard of them being the building blocks that make up matter before, so are we talking about the same thing? And yes, we are. All of these elements are atoms. Now, a hydrogen atom is different than a helium atom because of the number of those subatomic particles that I told you guys about in the intro. So, because a hydrogen atom is different in structure than a helium atom, they have different properties. So, because of those different properties, they are named differently. So, of course, a helium atom is different than an oxygen atom because you guessed it, they have a different structure, a different subatomic structure. And I'll clarify what makes each of these elements different. All right, guys, so let's get started with our atom model. And let's choose an element to work with. And I think I'm going to choose oxygen. So let's draw what you would see in a periodic table. You would see the letter O, that stands for oxygen. You would have the atomic number, and you would also have the atomic mass, which in this case is around 15.99. If we were to round, that would be around 16. And we measure atomic mass in AMUs, and AMU stands for atomic mass unit. So why do I want you guys to pay attention to those things? Well, because that's going to help me visualize the structure of an atom. So an atom has a nucleus. So what I'm going to do is I'm going to make an outline to let you guys know that everything that's inside the nucleus stays together. So there's two particles that we find inside the nucleus. That's the proton and the neutron. And figuring out how many protons you have is pretty simple. All you have to do is look at the atomic number. Our atomic number in this case is 8. So we're going to have 8 protons. So let's draw those protons. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 protons. So there's a couple of things that I want you guys to know about protons. Protons are positively charged. So they have a positive charge. And they have a mass of 1 AMU. Okay, so the next particle that we find in the nucleus is the neutron. How do we figure out how many neutrons we have? Well, it's not as simple as just looking at the atomic number, but it is pretty easy. All you have to do is subtract the number of protons uh, you have, so in this case it's 8, from your total mass, your total atomic mass. So that would be 16, right? So 16 minus 8 gives me 8 neutrons. So the reason we have to do that is because the number of neutrons won't always be equivalent to the number of protons you have. So we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. And in this case, the number of protons and neutrons is equivalent, but like I said, that always won't be the case. Um, those atoms that have different number of neutrons are called isotopes, but we're not going to focus on those today. So a couple of things that you guys need to know about the neutron. So the neutron has no charge, so no charge. And you might have guessed it from our math work, neutrons have a mass of 1 AMU. Okay, so just like the protons, and that's why we can use very simple math to figure out how many neutrons we have. Now, outside of the nucleus, you're going to find electrons. So electrons are so small, and let me draw 8 of those. 1, 2, 3, 4, 5, 6, 7, 8, and I drew them just scattered about randomly away from the nucleus um, for a reason. So they're very small. In fact, they're so small that their mass doesn't even affect our total atomic mass. Their mass is so insignificant, it's only a fraction of 1 AMU, that it doesn't affect our total mass. So they're very, very tiny. However, they are negatively charged. So they are negatively charged. So negatively charged. And what keeps them away from the nucleus is that charge. So you have positively charged particles in the nucleus that are repelling away the electrons. And they're flying across at super high speeds around the nucleus. And this is a little deceiving. You may think that, oh, it kind of looks like our solar system, planets, revolving around our sun. However, these orbits are very sporadic. They're incredibly just fast. Now, and they're actually a lot further away than this model suggests. If this nucleus were the size of, let's say, a golf ball, then the closest electron would be about a mile away from that golf ball. So they are actually really, really far apart. So that tells you a lot about the structure of an atom. It's mostly empty space. Now, in a neutrally charged atom, you would have an equivalent number of electrons as protons, and this is the basic structure that you guys need to know. So, just to recap, what we learned: a nucleus has protons and neutrons. Protons are positively charged, and you can find out the number of protons you have simply by looking at the atomic number. The number of neutrons is found out by simply subtracting the number of protons from the total atomic mass. They have no charge. And lastly, we have electrons floating, not floating, but flying at high speeds around the nucleus. And these electrons are, of course, negatively charged. And there you guys have it, the atom's basic structure. All right, guys, I hope you guys enjoyed this portion of your virtual field trip. I'll leave you guys with one little last fun fact about atoms. Hydrogen has no neutron. So in the periodic table, you'll notice that hydrogen has an atomic mass of 1, and that has to do with it just having 1 proton. Pretty cool stuff. I'll see you guys later.
Thank you. We did have one question, and Mr. Dominguez answered it right there at the very last. And the question was, what element has the atomic number of 1? And it is hydrogen. Now, Ms. Schramm is going to tell you about protons and valence electrons.
Good morning, everybody. It's me, Miss Schramm. So I'm going to share my little screen and we'll get started. Okay, so I am focusing on protons and valence electrons. So hopefully at the end of my section, you'll be able to identify that protons determine an element's identity and that valence electrons determine its chemical properties. So you just went over the anatomy of atoms and this atomic vocabulary with Mr. Dominguez, but just to review, we've got electrons, protons, and neutrons. Now, of course, neutrons are the subatomic oh my goodness. Okay, they're the particle that has a mass nearly equal to that of the proton, but no electrical charge. Okay, and they're present in all atomic nuclei except for those of hydrogen, which Mr. Dominguez just told you, hydrogen is the only one that does not have a neutron. Protons are the subatomic particles that have a positive charge, and electrons are those that have negative charge. And that's going to be my focus with you today. Okay, so first with the periodic table, if you look at the first one, the atom or the element that has the number 1 is hydrogen. That also dictates that they have 1 proton. Okay, then if you slide over to the other side, helium has 2. And you can go down again to lithium. Lithium has 3 protons. So that determines the element's identity. So as you travel through the periodic table, you'll notice that from left to right, the atomic number increases and so does the number of protons. Okay, so we're going to start with the atomic structure with hydrogen and helium. So neutrons and protons are held together in the nucleus by a strong force. Electrons are held around the atom by the, electrons are held around the atom by the attraction between the negative and positive charges. So as you can see, hydrogen, the red represents a proton, the yellow represents an electron, and there are no neutrons. Helium has 2 protons and 2 neutrons, that's in the nucleus, and then around are 2 electrons. All right, so we're gonna start filling out some drawings of different atoms. So first we have to talk about the energy shells or energy levels. In the middle, for the nucleus, I just have just 1 red dot to represent the nucleus because we're focusing on the electrons. So in the first shell, so you'll see the circle around, that represents the path that the first level of electrons travel. So there are 2 openings in the first shell. The next shell has 8, and the next shell has also 8. For our purposes, that's as big as we're going to get. So think of these energy shells or these little spots as parking spots. So if you're going to target, okay, just like the electron is trying to go to the nucleus, you want to park nearest to the store. So the electrons want to fill in the spaces nearest to the nucleus first. So that means the first shell will fill up with 2. Then once there is another electron, it will go to the next shell Once that spot is filled, it'll go to the next shell. So just remember, they always want to fill in closest to the nucleus first. Okay, so we're going to draw hydrogen. So here I have my little diagram. This stands for 1p plus. 1p plus is the shortened way to say 1 proton. Okay, so there's 1 proton in the middle, and we are assuming that the atom is balanced. So we are going to fill in one of those empty spaces with 1 electron. So I've changed it to yellow. So at this point, this is empty, and there's 1 proton, 1 electron, and that's it. Okay, so moving next to lithium. So once again, these are empty spaces in the shell, okay? So with lithium, I have the atomic number 3. That means I'm going to have 3 protons in the center, 3p plus, and we're assuming it is balanced for our purposes. So I fill in 3 electrons, filling up the first shell, then moving on to the second shell. All right, next we have sodium. Sodium is atomic number 11. So we have 11p plus at the center, and I'm going to fill in 11 spots. So I'm going to do 1, 2, then the next shell, and then move on to the next shell. So 1, 2, then I have 8. That's going to leave me with 10. So the outer shell is going to have 1 filled in to make my 11 electrons. Okay, so if we look at these atoms for the 3 elements we talked about, we have hydrogen, lithium, and sodium. They all have something in common. Now, if you shout it out, I won't be able to hear you, but maybe your friend next to you, you could tell them. What do you notice about each of these atoms? Hopefully you noticed that they each have just 1 on the outer shell. That outer shell is what's called the valence electrons. So the electrons in the outermost shell are the valence electrons. So each of these elements has 1 valence electron. There they go. So if you look at the periodic table again, the elements are taken out, but this is just kind of a basic map and layout. All of the elements in the first column going down have 1 valence electron. Then the next row, there's 2. There's a lot going on in the middle, so we skip the middle for our purposes today. When you hop over to the other side, there are 3, 4, and it goes on. And then the last row has 8 valence electrons, and those mean that their shells are full. So an element's most stable when its valence shell is full. Okay, so 3 things you need to know about valence electrons. Valence electrons are important indicators of an element's chemical properties. They are the ones gained, lost, or shared during a chemical reaction. And in general, like I just said, atoms are most stable and least reactive when their outermost electron shell is full. So that's like those elements in that last column. So we're going to check out a water molecule, H2O. And first we have the 2 hydrogen atoms. They have 1 proton, and then they each have 1 electron on the sides. Then we're going to bring up the oxygen. So H2, we have 2 hydrogens, and we're going to bring up our oxygen. Oxygen is number, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 8 electrons. And as you'll remember, the second shell has room for 8. Oxygen only has 6 electrons in its valence shell. So it has 6 valence electrons. Hydrogen each has 1. Now, if they combine, they're very easy to combine because oxygen needs 2 more to stabilize that outer valence shell. So hydrogen is the perfect match because it will complete the shell. So here's kind of what it looks like when those 2 react. Their chemical properties of hydrogen and oxygen easily react to make water because they stabilize each other's atoms. So here you can see now hydrogen has 2 valence electrons, so their first shell is full, and now oxygen has all 8 valence electrons, so their energy shell is full. All right, so my challenge to you is on a piece of paper, draw the atomic structure for the following elements and determine the number of valence electrons. So we have neon, whoop, that should say sulfur, sorry about that, fluorine and aluminum. All right, thank you, see you next time.
Thank you, Ms. Ram. And the question came in, how many electrons are allowed in the first ring? And I believe the answer, as she pointed out, is 2. And now Ms. Ramirez is going to tell you all about the periodic table.
Hello, my name is Ms. Ramirez, and we're going to be learning about trends within the periodic table and its arrangement. So before we get started, I have a neat little science toy here. It's a plasma globe or plasma ball. And essentially what we have in here are a mix of noble gases. And Ms. Schramm mentioned some of those noble gases in her lesson. So here we have our plasma globe. It's a mix of those various noble gases, and the colors that you are seeing are due to those noble gases of neon, argon, xenon, and krypton. And you can do some fascinating science experiments with these globes. So here I have a little LED bulb, and notice it's off right now, it's not plugged in, but as I make my way closer to our plasma globe, it will actually turn on, and you can see the little green light. So you might want to do a little research and see why is that. So I thought that was pretty cool there. So I'm going to go ahead and continue on with my presentation. Let me share my screen with you guys. I do have a couple of questions for y'all. Hopefully by the end of this presentation, you'll be able to answer these 2 questions. So please keep these 2 in mind. The first is, what do elements in the same group have in common? And the second is, describe 2 patterns or trends within the periodic table. So keep those questions in mind. So I'm going to show you some websites with some information. So let me pull up my websites. The first one that we're going to look at kind of shows us like the brief history of the arrangement of the periodic table. So we know that the Russian chemist Dmitry Mendeleev first arranged the elements in order of increasing atomic mass. And that is because the properties of those elements occurred in a periodic or regularly repeating pattern, hence the name periodic table. So we know that in the 1900s, though, a British scientist named Henry Moseley rearranged the table in order of the increasing number of protons, or the atomic number. So I thought it was interesting to compare the periodic table as it is now compared to the way it was originally formed. And so you can see here, this was the original periodic table. So think about some of those differences. So now let me show you guys the periodic table as we know it today. So let me change some of my settings here and pull up our periodic table. So y'all are probably familiar with this. The table itself is helpful because it makes clear patterns among the properties of these elements. So take a look at our periodic table and see what are some things that you guys can notice or identify. The first thing you should always do is always look for a key. So a lot of the periodic tables have a key that helps us determine whether things are metal or non-metal, whether it's a solid, liquid, or a gas. So if we take a look at this periodic table, we can sort it by metals. So you can take a look at what elements are metals. We can see what are non-metals. And then we can also sort it by groups and periods. So let's talk about what exactly those are. So we have the columns. Columns are also called the groups or families. And each vertical group or column, each element in the same group often have similar physical and chemical properties. So here we have group 1, group 2, group 3, 4, 5, and so on. Now remember, we were in our last group 18 with the noble gases that constituted our plasma ball. So here we have group 18, the noble gases. And because they all have similar physical and chemical properties, they're also known as families because they are very similar. So the property of elements in a group are similar because the atoms of these elements have the same number of valence electrons. So remember, Ms. Schramm went over that. The next part of our periodic table we have are the periods, and those are simply the rows. So take a look at some of these rows. We have row 2, 3, 4, 5, and so on. Rows are also called the periods because the physical and chemical properties of elements will change in predictable ways from one end of the period to the other. So that's where we can get some of our trends. So for example, within any given period, the atomic size will actually decrease as we move from the left side to the right side. The size will decrease. Also, we'll notice changes in density. So the most dense elements are actually going to be in the middle of the periodic table, and then towards the left and the right ends, you're going to have your least dense elements. So then let's take a look at, we know earlier that the elements are arranged in order of increasing atomic numbers. So we talked about that with Mr. Dominguez. We have our atomic numbers over here. So you can see that they are arranged in increasing atomic number. And then on the bottom, sometimes people forget these, we have the lanthanides and the actinides, and they're simply placed below the table just to make more room. So there they are highlighted in our web page. So the next thing I want to show you are some more periodic trends. And so the first thing that you'll notice, we have increasing electronegativity as we move across the periods. So as we're moving from the left to the right end, electronegativity is increasing. We also notice changes in ionization trends. So here's another example. Remember our atomic numbers from the periodic table down here. And then let me scroll down. So here's our periodic table again with the increasing ionization energy increasing as you're moving from the left side to the right side. And remember, these rows are called your periods. Another trend we have is the electron affinity trends. And as that name suggests, electron affinity is just the ability of an atom to accept or take in an electron. So if we take a look at our little diagram here, we can see that the electron affinity will actually increase as you're moving from the left side to the right side. So that's another trend. As we move on down, we talked about this a little bit earlier. We have the atomic radius trends. So notice our arrows switch this time. So when we're going through our periodic table, as we're moving from the right to the left side of the periodic table, the atomic radius will actually increase. So pay attention to those arrows. Those are very important for the trends. We also have other trends like melting point trends, metallic character trends, and we'll go over some of those briefly when I show you some other apps that will help you with these trends. So let me go back to our slide presentation, and I'm actually going to show you guys a few of these apps that you can use to help you further explore some common periodic trends. The first one that we're going to take a look at is Mendeleev.me. It's not free, but it's still kind of cheap. These other three apps are free, and I do recommend you guys use them to help you explore those trends. So I'm going to go ahead, and I did a pre-recording of me exploring those apps. So let me play for you that little video. So here we are. The first app we're going to take a look at is the Mendeleev.me app. This is the one that's not free, but it has a lot of information on it. So here's an example. I clicked on helium. It shows you all about the properties, physical properties, reactivity, its classification, and the various properties and uses of each of these elements. The next one we're going to take a look at is one of the free apps, the periodic table app. This is the one that I recommend you guys get because it does go into great detail about the various trends within the periodic table. Again, this one is free, but it has lots of videos, podcasts. If you're not a reading person, you can listen to the information. But here's some of those trends: boiling point trends, melting point trends, the electronegativity that we talked about, the density, ionization energy. I got to work on saying that word. But it shows all those other trends within the periodic table. So I do recommend that app from the Royal Society of Chemistry. You can also look at the different groups the different periods, and the classifications, whether it's a metal or a non-metal. The next app we're going to look at is a very simple one. It's the K12 Periodic Table of Elements app. This one's very simple, but it does show the Lewis dot structure. And then the last one is the Periodic Table 2021, also another simple app, but it does give you information on those electrons and how they're located, where they're located, the uses and the simple properties of each of those elements. So I'm going to go ahead and move over to our next slide. Hopefully you guys take time to use some of those apps, but I have a challenge for you guys. I would like for y'all to research an element and see if you can answer some of the questions on the slide, and maybe even use some of those free apps to help you research those elements. One of the elements that I am probably most familiar with is xenon, and I hate cars that have those new xenon headlights because they are super bright and it makes it a pain to drive at night because it's so blinding. So that's one of the elements that I kind of was familiar with and took an interest in. But research an element that interests you and see if you can answer those questions. The last thing I have for you guys are just some YouTube songs that you can look up later. There's one on the periodic table. It goes through all the elements in the periodic table. And then the other one is the periodic table song that goes through some of those trends, and that's by Mr. Parr. So I'm going to go ahead and stop my screen share, and that's all I have for you guys for the periodic table. We're going to give it back to Dr. Gorman to answer any questions.
Thank you, Mr. Ramirez. Boy, that was a lot of information. And the question came in. It was already answered, I believe, but who made the first periodic table? Who designed it? It was the Russian Mendeleev. Now, earlier, Mr. Monroe talked about the distinguished looking gentleman that he introduced. I saw the picture of this Russian Mendeleev, and distinguished looking gentleman was not a term or not a phrase that I would attach to Mr. Mendeleev. However, he did get us started. Okay. During this virtual field trip, students observe the structure of atoms. Students learn the protons, determine an element's identity, and valence electrons, determine its chemical properties, including reactivity. Students also interpreted the arrangement of the periodic table, including groups and periods, to explain how properties are used to classify elements. Mr. Monroe told you about the history of atoms. Mr. Dominguez, the structure of atoms. Ms. Schramm covered protons and valence electrons, and Ms. Ramirez just told you all about the periodic table. Thank you. If you have questions or if you have comments, go to www.tiny.cc/6-8 feedback. Fill out a very short form and send it back to us. We would appreciate it. Thank you very much. And you have a great day and a great year.